Hello everyone, myself Rakesh M from Sri Venkateswara College of Engineering. In this video, we are going to discuss a topic on subject network analysis. In this video, we are going to discuss a topic about Laplace transformations and applications in network analysis. This representation explores the powerful Laplace transform and its applications in network analysis, covering fundamental concepts, problem solving techniques, and practical examples. Introduction to Laplace transformation. Definition: the Laplace transform converts a time domain function to a complex frequency domain function. Applications: used in network analysis, control systems, and solving differential equations. Properties of Laplace transforms: linearity, time invariance, differentiation, and integration. Linearity: transform of a linear combination is the same combination of individual transforms. Time invariance: time shifting in the time domain corresponds to multiplication by an exponential term in the frequency domain. Differentiation: the transform of a derivative is related to the transform of the original function and its initial conditions. Integration: the transform of an integral is related to the transform of the original function. Inverse Laplace transforms. Definition: the inverse Laplace transform converts a frequency domain function back to a domain function. Methods: partial fraction expansion, contour integration, and table lookup methods are commonly used. Solving differential equations using Laplace transforms. Transform the equation. Solve for the transform variable. Inverse transform. Transform the equation. Apply the Laplace transform to both sides of the differential equation. Solve for the transformed variable. Algebraically manipulate the equation to solve for the transform of the unknown function. Inverse transform. Apply the inverse Laplace transform to obtain the solution in the time domain. Transient, transient analysis of RLC circuits. Initial conditions. Apply Laplace transform. Solve for circuit variables. Inverse Laplace transform. Initial conditions. Specify the initial voltage across a capacitor and current through the inductor. Apply Laplace transform. Transform the circuit equations using Laplace transforms to the frequency domain. Solve for circuit variables. Solve the transformed equations for the circuit variables in the frequency domain. Inverse Laplace transform. Apply the inverse Laplace transform to obtain the time domain responses of the circuit. Frequency domain analysis of networks. Impedance. Impedance is the complex frequency domain equivalent of resistance. Circuit analysis. Apply Kirchhoff's law and other circuit analysis techniques using impedance. Frequency response. Analyze the network's behavior at different frequencies. Bode plots. Graphical representation of a network's frequency response. Transfer functions and pole zero plots. Transfer function. The ratio of the output signal transform to the input signal transform. Poles and zeros. Points in the complex plane where the transfer function has infinite or zero values. Pole zero plot. Graphical representation of the poles and zeros of the transfer function. Stability. The location of Poles and zeros determines the stability of the system. Laplace transforms in control systems. System modeling. Use Laplace transforms to represent control systems in the frequency domain. Stability analysis. Determine the stability of control systems by analyzing poles and zeros. Controller design. Design controllers to achieve desired system performance based on frequency domain analysis. Conclusion and key takeaways. Laplace transforms provide a powerful tool for analyzing and solving problems in network analysis. They simply complex they simplify complex calculations, reveal system characteristics in the frequency domain, and facilitate controller design. By applying these techniques, engineers can design, analyze, and optimize networks effectively. So, this was about network analysis and Laplace transformation and applications in